Hello, welcome to physical chemistry tutorial number 2. Today we're going to talk about properties of wave functions. So wave functions are functions that satisfy 4 mathematical properties. They must be single-valued, continuous, differentiable, and bounded. So the first requirement is that the function must be single-valued, and essentially what this means is that the function must pass the vertical line test. So let me draw 2 functions. Okay, so what the vertical line test basically means is that if I draw any, this is a keyword, any vertical line, and the vertical line only touches the graph once, or the function once, then that function passes the vertical line test. Here you can see I have a vertical line which touches the function twice, so this is not single-valued. So this is not an acceptable wave function. On the right hand side, however, if I draw any vertical line, it will only touch the function once. So this is single-valued. So this is an acceptable wave function. A wave function also must be continuous. So the function cannot contain jumps, holes, or vertical asymptotes, and these are called discontinuities. Discontinuities. So let me give you an example of each. So this is a jump. And then we have the hole. And then finally we have the vertical asymptote. So in all cases, in order to draw each of these functions, I have to lift my pencil at least once. So that's a good way to determine if your function is continuous. If you have to lift your pencil at least once to draw the function, then it's not continuous. So the function must also be differentiable, or the derivative must be continuous. And the way you can check this is to see if the graph has any sharp corners or turns. So if the graph does have sharp corners or turns, then it's not differentiable. So let me give you an example. So here is f of x is equal to the absolute value of x. And here is a sharp corner / turn. So this function is not differentiable at this point. So this is an unacceptable wave function. So the function must also be bounded. What this means is that the range, not the domain of the function, cannot approach infinity. So let me give you an example. If we have f of x is equal to x squared, where x is in the reals, or the domain of x is negative infinity to infinity, this is not bounded. if I take the limit as x approaches infinity of f of x, I would get infinity squared, which is infinity. So the range approaches infinity. So this is not a bounded wave function. One way to get around this is to restrict the domain. So if I said f of x is equal to x squared, where x is only defined from 0 to 10, that would look like this. And in this case, the function is bounded because f of x never approaches infinity. There are additional requirements for wave functions. For example, they must be eigenfunctions of the Schrodinger equation, but we'll talk about that later.